All right. Hi, everyone. My name is Corey Carpenter. I am working on Aerospace Project 3 with Highspeed Aerodynamics. And today I'm going to show you a angled flat plate with a flap at 5 degrees, a 5-degree flap and a 10-degree plate. And we're going to calculate the velocity, Mach number contours, and pressure contours of it and find the coefficient of lift and drag. All right, so first, we're going to start off and go to geometry. We're going to start there to set up our geometry. Let me switch over my screen. All right, so for our geometry, we're going to go with a giant square around our airfoil, which is going to be represented by this. This is as skinny as I can get it, with it representing a line. It's not going to be completely accurate to just doing it as approaching it as a line, because there's no way to actually simulate that. So I made it as small as I can. This is about 10 centimeters in length, and then this is about 3.33 centimeters, which is about a third of the main thing. And this is angled at 10 degrees from the X-plane, and then the flap is angled at 15 degrees with the X-plane, or 5 degrees from this 10-degree angle right here. All right, so next we're going to go and switch our screen over to our meshing. All right, so you should be seeing this now. Let's see. Yep. All right. So this is going to be our meshing. We're going to go to mesh. We're going to make this 0.0004 or 1, and to make it as small as we can to get this as fine as of a mesh we can get around this airfoil design. All right. After that, we're going to go to wall. We're going to name this entire airfoil as the wall, just so that we can calculate the coefficient of lift and drag upon it, and make sure everything is selected upon it. And next, we're going to name the outside area the far field, and this will be able to calculate our Mach number going over the entire airfoil. From here, we're going to go to our setup, and we're going to set it up using double precision. We're going to go to Fluent now. All right, right here is Fluent. Already got a little loaded, but first you're going to want to go to Models, do Inviscid, and then Energy On. You need your energy equation. Go to Fluid, go to Air. Make sure it's set to ideal gas where it won't calculate correctly. And also, before I forget, you go to General and make sure it's density based. After that, you're going to go to, let's see, your boundary conditions is going to show up, your far field is going to show up as a wall. Convert that to far field and you'll be set to go. And it'll become your inlet. Set it to the Mach number you want to use. I'm using 2.2 just to make sure everything is all okie dokie artichoke with the project. And we're going to go to, let's see, go to initialization. And we're going to hit initialize. I already did that. And then we're going to go to contours, run calculation. You're going to want solution steering. Select that. You can only do that with Inviscid, and then select supersonic, so it'll steer the solution towards the supersonic answer and make it way more accurate and quicker. Hit calculate. Should take about 300 iterations, and you should go to contours after that. And let's say we want pressure. So we hit that. Bam, we got our pressure. Let's see that a little bit better. Hide that over. And it disappeared. All right, cool. Let's do it again. Bam. Here's our pressure. So as you can see, there's a little bit of stagnation pressure at the front because it is indeed not aligned. So there's going to be a little bit there at the point right there. And it's going to create a shock wave right there from that. And then there's going to be a little miniature shock wave towards the end of this, towards the leading edge or trailing edge. And then the little bitty buddies there. And let's go check our velocity. Here's our velocity contours, which is pretty much the opposite of pressure. And we can also check from here our Mach number. So go here, here's our Mach number. And as we can see, we have a lot higher Mach number right here at the top of it as it kind of gets into a shockwave cone from here, which is about 2.2, and then bam. And I should see it slows down here, but faster right over here at the top of it. Now we want to find our coefficient of lift and drag. So we're going to go to reference values, or actually report definitions, and create a new one. So create new force report, lift or drag. I'm going to go to drag, make sure 1, 0, and then drag coefficient, and then hit compute. First select wall, then compute. And you get your drag coefficient, which we got 726, which is a lot higher than our theoretical solution, but I believe that is because of the thickness, along with we actually inputted a length, while the other one disregarded the length within the formula. Now, this calculated the actual force of it, while the other one was theoretical. Lastly, I'll show you how to do the last one, which is coefficient of lift, force report, lift, select the wall, and compute. Bam. Okay, we got 2963 for our lift, which is again higher than what we predicted, but that is because of the thickness and the fact that we actually gave it a length and it calculated the forces all together, like in the summary, and it didn't disregard the length like the theoretical did. Thank you so much for watching. Next, I'll show you the second airfoil, and have a nice day.